Alright, this is Jahangir from Medporium, and today we'll talk about the urinary system, specifically part 3 of the urinary system. In part 3, we'll discuss the second step of urine formation, which is tubular reabsorption and secretion. Now to start, let's talk about the second step of urine formation, which involves the conversion of glomerular filtrate to urine, which involves the removal and addition of chemicals by tubular reabsorption or secretion. Now to talk about tubular reabsorption and secretion, we need to start at the proximal convoluted tubule, also known as a PCT. The PCT reabsorbs 65% of glomerular filtrate and removes waste from the blood and puts that waste into the renal tubule. They have microvilli, which increase surface area and absorption. So the proximal convoluted tubule is most involved in the reabsorption of the glomerular filtrate. If you don't remember the anatomy or the location of the proximal convoluted tubule, please head over to the first part of the urinary system. Alright, now let's move on over to the tubular reabsorption. Well, tubular reabsorption is a process of reclaiming water and solutes from the tubular fluid and returning it into the blood. There are two routes of reabsorption. The first includes the transcellular route, which involves substances passing through the cytoplasm of the tubule epithelial cells and out of the base of the cell. So to put this in basic terms, the solute or the substance passes through the cell, and that's called the transcellular route. Second, we have the pericellular route, which is the process of substances passing through the gaps, also known as tight junctions, between the epithelial cells. The main thing to understand about tubular reabsorption is that it's a process of taking that necessary water and solutes from the tubular fluid and putting it into the blood, in which the blood takes it all the way throughout the body. Tubular reabsorption is a significant action the nephron performs that is very crucial for our body to function. To really understand tubular reabsorption, let's move over to the Thinkpad. So we're at the Thinkpad and we want to understand tubular reabsorption. Well, let's go back to our notes and let's remember the two routes of reabsorption, which include the transcellular route, which is when substances pass through the epithelial cell and then into the tissue fluid and then peritubular capillary, and second, the pericellular route, in which the substance passes through the gaps, also known as tight junctions, between each epithelial cell. Now let's talk about the solutes that are involved in reabsorption or are reabsorbed. We'll start by sodium chloride. So there are two types of transport proteins on the apical cell surface that are responsible for sodium intake. The first includes symports, which take part in transport of two different molecules or elements at the same time. So I'm just going to draw the function of a symport. So since we're talking about the sodium glucose transport protein, I'll illustrate it right here. So let's say we have our sodium right here, and let this G just represent glucose. I'm just too lazy to write the chemical formula because it's very long. So for a symport, it would take both molecules together at the same time. Either one of them is bound to each other or not. In the sodium glucose transport protein, sodium is bond to glucose in order to bring sodium into the cell. So that's what a symport looks like. Second, we have an antiport. So I'll just illustrate what an antiport looks like. And since we have our example, let's talk about the sodium hydrogen antiport or sodium hydrogen ion antiport. And an antiport is just involves in the exchange of one molecule or element from another. Think of this as trading. You can only get one thing. Now for the sodium hydrogen antiport, we can only get sodium if we exchange hydrogen ions. So then the tubule epithelial sees this and says, wow, that's a great bargain. And then they give away these hydrogen ions for sodium, so sodium can go into the tubule epithelial cells. Now this exchange results in a very acidic tubular fluid, which results in an acidic urine. Now hydrogen ions make the tubular fluid and urine acidic. Once we go into the water, electrolyte, and acid-base balance unit, we'll talk about the effects of too much hydrogen ions or too little hydrogen ions. So now let's move over to the two types of transport proteins responsible for chlorine intake. Now, the first one includes the chlorine anion antiport. Now, as we talked about, an antiport is just an exchange of one molecule for another. So to illustrate this, let's just say this is our chlorine and this is our anion. There will be a switch. Since the cell wants chlorine, it'll exchange an anion and put it back into the tubular fluid. And this is the location of the chlorine anion antiport. This is the location of the sodium hydrogen antiport, and this is the sodium glucose transport protein, also known as SGLT. So now let's talk about the second transport protein responsible for chlorine intake, which is the potassium chlorine symport, which is right over here. And this involves chlorine and potassium moving from the cell to the peritubular capillaries. And as we talked about a symport takes part in the transport of two different molecules or elements at the same time. So just think of this as potassium and this as chlorine. And they're just moving together. Now let's talk about the sodium-potassium pump. Now, I like to think of the sodium-potassium pump as the mother of the epithelial cell, or the guardian, because they prevent the accumulation of sodium into the cell by pumping sodium out of the cell through the tissue fluid and into the peritubular capillaries. Now the thing to note is that chlorine ions follow sodium because they are negatively charged. And as shown in the bond, sodium has a 1+ charge and chlorine has a -1 charge. And they bind together, forming sodium chloride. I think you know this already. If you didn't, you just learned something new, and good for you. So now let's talk about glucose, one of the solutes that are also reabsorbed. Now glucose, as I talked about before, from the SGLT or sodium glucose transport protein, they are co-transported with sodium in the sodium glucose transport protein. Now, for a healthy adult or child or just a healthy person in general, usually all glucose is reabsorbed, but sometimes that's not the case. We'll talk about when glucose isn't or is little reabsorbed throughout the video. Now let's talk about water. Now water is reabsorbed through the pericellular route by solvent drag. And solvent drag is a process in which water carries all these other solutes. So it's basically like LeBron and the Cavaliers. He was just carrying them to the finals. Think of that as solvent drag. Now there's also another way for water to go through the tubule epithelial cells, which is the transcellular route. And the thing that's involved in the transcellular route is called an aquaporin, which are channels on the apical part of the cell that allow water to enter the tubule cell and leave the cell. So just highlighted right here. Here is what an aquaporin is. Just a channel for water to come in. So now let's talk about urea. And as we talked about before, urea is a very high nitrogenous waste. It's very wasteful, and it's very bad for our body if it stays in our body. So urea is reabsorbed with water from the solvent drag, and there's more urea in the urine rather than blood. since this is a nitrogenous waste and we don't need it. Now let's talk about the other electrolytes, the last one. So other electrolytes, which include uric acid, magnesium, calcium phosphate, they pass through the pericellular route with water, which is solvent drag, as I talked about before. Alright, so we just wrapped up our discussion from the Thinkpad about tubular reabsorption. Now let's talk about the uptake by peritubular capillaries. And to do that, let's go to the lovely Thinkpad. Alright, so we're at the Thinkpad and we want to understand the uptake by peritubular capillaries. Well, we first need to discuss the three factors that promote osmosis in the peritubular capillaries, which also influence the uptake by the peritubular capillaries. We'll start by the first factor, which is bulk flow. And this is the accumulation of reabsorbed fluid. Let's just say that these circles are just the accumulation of reabsorbed fluid at the base of the epithelium, creating a high tissue pressure that drives water out into the capillaries. So that high pressure just pushes water into the peritubular capillaries. Now we will talk about the second factor of promoting osmosis into the peritubular capillaries, which involves the narrowness of the efferent arteriole. This can also be created by angiotensin II, we'll cover that later, which lowers the blood hydrostatic pressure from 60 millimeters of mercury just to about 8 millimeters of mercury. So there's a lower blood hydrostatic pressure, which equates to a lower resistance for blood to be reabsorbed. So this low blood hydrostatic pressure just makes the water, you could just say happy, and the water just moves from the tissue fluid into the peritubular capillary. So there's no resistance or negative person to tell them not to. Now let's talk about the third factor, which involves leftover blood proteins, creating a high colloid osmotic pressure, which helps push water out into the peritubular capillaries. So both of these factors account for the osmosis of water. The main one, as I talked about, bulk flow. Then there's the low blood hydrostatic pressure, and then the high colloid osmotic pressure. So now let's talk about the influence of angiotensin II secretion on the uptake of peritubular capillaries. So we'll just start by angiotensin II being secreted, then there's a constriction of afferent and efferent arteriole, more of the efferent arteriole, which reduces glomerular blood pressure and filtration, and reduces the blood pressure in the peritubular capillaries. As I discussed before, there will be a low blood hydrostatic pressure, which, as I talked about before, reduces resistance to tubular reabsorption. And the high colloid osmotic pressure influences the water to just push through the peritubular capillaries. And then the outcome comes out to tubular reabsorption increasing, and urine volume is less, but concentration is high, which is what we want. We want to savor or extract as much water as we can from the renal tubule and put it back into the peritubular capillaries, so then urine can be very, very concentrated. Alright, so we just finished our conversation about the uptake of peritubular capillaries for reabsorption from the Thinkpad. Now let's talk about the transport maximum for reabsorption. Now the transport maximum is a maximum rate of reabsorption at which the transporters are saturated or full. Each solute reabsorbed by the renal tubule has their own transport maximum. To understand the transport maximum, let's move over to the Thinkpad. Alright, so we're at the Thinkpad and we want to understand the transport maximum. Well, to understand the transport maximum, let's talk about glucose. In normal glycemia or normal levels of glucose, urine is mostly glucose free, and most glucose is being reabsorbed. So the glucose transport proteins are doing its job. There are there's no glucose left in the urine as it is always being reabsorbed in a healthy patient. But with hyperglycemia, which is an elevated level of glucose, in hyperglycemia, there are blood glucose levels above 220 milligrams per deciliter, in which glucose is filtered faster than the renal tubules can reabsorb, meaning the glucose transport proteins can't filter all of this glucose, which what happens? The transport maximum is reached, and a lot of glucose is not reabsorbed, and all of that glucose will show up in urine, which is called glycosuria, when there is glucose in the urine, which is abnormal. There should not be glucose in the urine. This is a sign of diabetes mellitus. So we just finished our conversation about the transport maximum in the Thinkpad. Now let's talk about the nephron loop. The primary function of the nephron loop is to generate an osmotic gradient that enables the collecting duct to concentrate urine and conserve water. So we'll start by the descending limb and the thin segment. So both the descending limb and the thin segment are permeable to water but impermeable to solutes. They usually prioritize on reabsorbing water. But that's a different case when we go all the way up to the thick segment and the ascending limb. Cells in the thick segment have proteins in the apical membranes that bind sodium, potassium, and chlorine from the tubular fluid and into the cytoplasm of the tubule cells. So when I talked about the primary function is generate an osmotic gradient, the nephron loop reabsorbs all those solutes, including urea, which generates the very salty and very high osmolarity medulla, which helps the collecting duct reabsorb water. So the thick segment is impermeable to water, meaning water cannot follow reabsorb electrolytes, which equates to the tubular fluid becoming more diluted by the time it reaches the distal convoluted tubule. So just remember, the nephron loop, there's different parts of the nephron loop, the descending limb and the ascending limb. Descending limb is permeable to water, impermeable to solutes, but ascending limb is impermeable to water and permeable to salts. So now let's move over to the distal convoluted tubule and the collecting duct. To understand the distal convoluted tubule and the collecting duct, we need to move over to, you guessed it, the Thinkpad. Alright, so we're at the Thinkpad and we want to understand the distal convoluted tubule and the collecting duct. Well, first I want to talk about the fluid composition. And the fluid arriving to the distal convoluted tubule contains 20% water and 7% solutes. And as we talked about before, this is because of the ascending limb, as it is impermeable to water. Now the distal convoluted tubule is somewhat impermeable to water, but some water can be reabsorbed. Now the thing that's very significant to learn about the distal convoluted tubule and the collecting duct are that they reabsorb by regulation of hormones. We'll talk about what hormones they're regulated by later. Now let's talk about the two kinds of cells in the distal convoluted tubule and the collecting duct. The first includes principal cells, which are most abundant cells with receptors for hormones and involved mainly in salt reabsorption and water imbalance. The second is intercalated cells. They are few in number, but they reabsorb mainly potassium and secrete hydrogen ions into the tubule lumen. They are also involved in acid-base balance, as we will talk about in the water electrolyte and acid-base balance unit. So to summarize this whole kind of nephron, the physiology, the proximal convoluted tubule kind of works on reabsorption mainly. The loop of Henle tries to create an osmotic gradient for the collecting duct. Distal convoluted tubule and the collecting duct mostly reabsorb, but by regulation of hormones. So just remember that. Alright, so we just wrapped up our conversation about the distal convoluted tubule and the collecting duct from the Thinkpad. Now let's talk about the major hormones that influence the rate of reabsorption or overall reabsorption by the distal convoluted tubule and the collecting duct. We'll understand that by moving on to the Thinkpad. So we're at the Thinkpad and we want to understand the major hormones that regulate the actions or the reabsorption of the distal convoluted tubule and the collecting duct. We'll first start by aldosterone. Now aldosterone is referred to as the salt-retaining hormone. Aldosterone is a steroid secreted by the adrenal cortex when blood sodium levels are low or it falls, or the potassium concentration of the blood rises. Now, aldosterone acts on the thick segment of the ascending limb, the distal convoluted tubule, and the cortical portion of the collecting duct. Now, aldosterone stimulates each segment to reabsorb sodium while also secreting potassium. And overall, aldosterone elevates blood pressure since water follows salt, which elevates blood pressure. Now, as we talked about before in the renin-angiotensin-aldosterone mechanism, angiotensin II stimulates the secretion of aldosterone from the adrenal cortex. Now let's move over to the second hormone that regulates the reabsorption of the distal convoluted tubule and the collecting duct. Alright, so now let's talk about the second hormone that regulates reabsorption by the distal convoluted tubule and the collecting duct, and that hormone is called the natriuretic peptides. Now, natriuretic peptides are hormones secreted by the heart in response to a high blood pressure. Now, there are two different types of natriuretic peptides. One of them is the atrial natriuretic peptide, also known as ANP, and the other is the brain natriuretic peptide, also known as BNP. Now today we'll just talk about what the impact or what the natriuretic peptides do towards the urinary system. Well, the natriuretic peptides excrete four actions that result in the excretion of more salt and water in the urine, which lowers blood pressure and blood volume. The whole purpose of natriuretic peptides is to lower blood pressure and blood volume. Now, the excretion of more salt through the urine is called natriuresis, and the more secretion of water in the urine is called diuresis. So now let's talk about the four actions. The first one includes the dilation of the afferent arteriole. So let's just say this is my afferent arteriole, and they also constrict the efferent arteriole. So let's just say this is my efferent arteriole. Let's just say this is my renal corpuscle, renal tubule. So in dilation in afferent arteriole increases the glomerular filtration rate since there's a higher blood flow. Now this high blood flow and this high glomerular filtration rate forces fluid to flow rapidly throughout the renal tubule without having time to reabsorb, which is actually good since natriuretic peptides stop the reabsorption of sodium, and the reabsorption of sodium influences the reabsorption of chlorine and then the reabsorption of water, which all in all increase blood pressure. So they try to inhibit that by increasing the glomerular filtration rate. Now let's talk about the second action. And the second action is they antagonize the renin-angiotensin-aldosterone mechanism. And as we talked about before in part 2, this mechanism increases blood pressure. And the natriuretic peptides will do anything to decrease blood pressure. So they inhibit renin secretion and aldosterone secretion. Now, as we talked about before, aldosterone is secreted by the adrenal cortex, and natriuretic peptides try to stop this secretion, because overall these hormones increase blood pressure, and the natriuretic peptides want to decrease blood pressure, so they'll do anything to stop the increase of blood pressure. The third action is they inhibit the secretion of antidiuretic hormone, also known as ADH, and its actions on the kidneys. Now we'll talk about the antidiuretic hormone later, but just to give it to you in a nutshell, it's a water retaining hormone. And as we talked about, if water is retained, there's a high blood pressure. Now the fourth action is that they stop salt reabsorption by the collecting duct, as I talked about before, since if there's a salt reabsorption, water follows, which increases blood pressure. So the thing to remember is that the natriuretic peptides try their best to lower blood pressure when there is an increase in blood pressure. They try to lower it back to normal. So now let's talk about the antidiuretic hormone. Alright, so let's talk about the antidiuretic hormone, or ADH, which is also known as the water retaining hormone. Now, ADH is secreted by the posterior pituitary gland in response to dehydration and a rising blood osmolarity. So to really understand the antidiuretic hormone, let's draw ourselves a collecting duct. It doesn't have to be the best collecting duct. I might even have the ugliest collecting duct. But let's just draw ourselves a collecting duct. Let's just say that this is a collecting duct. Now, ADH makes the collecting duct more permeable to water, which makes reabsorption of water much more easy. The reabsorption of water is higher and is much easier than before. So this reabsorption of water is taking, let's just say this is our peritubular capillary. Water is taken through the peritubular capillary and then throughout the body, restoring hydration and lowering the blood osmolarity to normal. So the antidiuretic hormone overall just influences water reabsorption. So now let's talk about the parathyroid hormone. Alright, so now let's talk about the fourth and final hormone that regulates reabsorption of the distal convoluted tubule and the collecting duct. And that hormone is called the parathyroid hormone, also called PTH, which maintains calcium homeostasis and is secreted by the parathyroid gland, just right over here, as you can see. Now, the parathyroid hormone is stimulated from hypocalcemia, in which it stimulates the parathyroid gland to secrete PTH, also known as parathyroid hormone, which restores calcium homeostasis by inhibiting phosphate reabsorption and acting on the distal convoluted tubule and the thick segment of the nephron loop to increase calcium reabsorption. So to show that, let's just draw ourselves the thick segment of the nephron loop. Doesn't have to be the best thick segment. And then the distal convoluted tubule, represented by these kind of waves. You can also draw the collecting duct if you want, but that's optional. Alright, so we have our distal convoluted tubule and we have our thick segment of the nephron loop. So as we talked about, the PTH or parathyroid hormone inhibits phosphate reabsorption. So we have phosphate right here, and the parathyroid hormone rejects their invite into the reabsorption. They also act on distal convoluted tubule and the thick segment of nephron loop to increase calcium reabsorption. So basically, parathyroid hormone hates phosphate but will allow in calcium reabsorption. So overall, the parathyroid hormone increases phosphate content in the urine and decreases calcium content in the urine, minimizing further decline in blood calcium levels. So the one thing to learn from here is that the parathyroid hormone just maintains calcium homeostasis and tries to savor or extract or minimize the decline of the blood calcium levels. We'll talk about the parathyroid hormone when we talk about the skeletal system. In the skeletal system, the parathyroid hormone has a much more significant impact, but today we only talked about the urinary system. Alright, so that wraps up part 3 of the urinary system. I know this is the end of a good thing, but hey, we did cover the second step of urine formation, which is tubular reabsorption and secretion. And as always, a Pomodoro a day makes you a doctor one day. I'll see you next time.